Hello everyone, welcome to Group 25 CDR presentation of our senior design project. Our project is called the Interactive Cat Toy. The members of Group 25 are two electrical engineering students, including myself, Bong Wing, and Elizabeth Vargas, and two computer engineering students, Joseph Lopez and Eliza Grabowski.
We are very thankful to have a sponsor working with us on our senior design project. Lei Fan is a mechanical engineer and author who is generously giving his time to take care of the mechanical design and the 3D printing of the chassis for our project.
With 373 million cats domesticated as pets around the globe and approximately 93.5 million of them in the US, this provides a large number of pet owners looking for a toy to entertain their fun-loving felines. Cat toys allow pet owners to have fun and enjoy their time with their cats, while also helping their beloved felines with their well-needed exercise. Finding the right toy to really attract a cat into playing, however, can be a really tough challenge. Our senior design team decided to meet this challenge by building an interactive cat toy that entices cats into playing using various luring features.
Goals and objectives. With this project, we want to design an interactive cat toy that cats can be entertained by and engage in play with for hours. We also want to incorporate elements into our toy that are key to domestic cat entertainment. Work to implement the current standards and the best safety factors that we can. Also, we want to design our ICT so that it can withstand rough cat plays and last for a reasonable amount of time.
We performed market and product research to help us plan the design for our interactive cat toy. This research helped us to identify key features that were proven to entertain cats. We planned to incorporate all of the key features that we identified into our interactive cat toy. But we also take our toy design further by adding control of select features to a phone application.
These are some of the important requirements specification for the interactive cat toy. The highlighted are the requirements that we'll be demonstrating. The LEDs for our lighting effect need to be bright enough to be seen clearly in a room with typical daylight brightness, while not being too bright to cause damage to a cat's eye. The response from our motion detector should activate device features within a reasonable distance, and our phone application should not have an excessive delay time. For the toy, we have three hardware layers. The outermost layer is the interchangeable exterior skins. The middle layer is a protective chassis, and the innermost layer is electronics with the PCB and its components.
We decided to construct two interchangeable exterior skins for the interactive cat toy. The exterior skins are designed with the same measurements and a zippered opening so that the chassis can be switched easily between them. The chassis for our toy is designed to protect the electronics of the toy, to support toy features, and to be easily switched between the toy's interchangeable skins. The mechanical design and 3D printing of our chassis is being done by our wonderful sponsor, Lei Fan.
Hardware level 3 consists of the electronics and the PCB. Within the PCB, we have a voltage regulator for the battery with a switching circuit for charging. The PCB also have a microcontroller, Bluetooth module, and other components, such as motors, sensor, and speaker. To test the components of the toy, we decided to use the Raspberry Pi Pico for breadboard testing. The Raspberry Pi Pico also used the same microcontroller as our prototype, hence making it easy for us to transfer our work onto the PCB. This is the hardware block diagram of our system. We have several regulators implemented in our design due to the voltage requirements of different components. The battery will be regulated first to 5.2 volts, The 5.2 volts will be used as the system voltage. It will power the LED lights, the motor, and the Bluetooth module. Then that voltage will be passed on to another regulator to convert it to 3.3 volts. The USB also put in here so that we can program the microcontroller through the USB. The 3.3 volt is used to power the microcontroller and the PIR sensor. Notice that we also have another 5 volt to 3.3 volt converter. This converter is primarily used to power the speaker. The speaker needs a clean voltage source. It helps to reduce the digital noise from the other components to produce a clearer sound. This is the schematic of our prototype. We have the battery regulator, USB and 3.3 volt regulator, an audio regulator, microcontroller, crystal oscillator, and the flash memory for the microcontroller. For the microcontroller, we use RP2040 for the prototype and the Raspberry Pi Pico for testing. It consists of 26 general purpose IOs. The operating voltage is 3.2 volt DC. The operating temperature ranges from -20 to 85 Celsius. For this project, we primarily use CircuitPython to program the microcontroller. This is the layout of the PCB. The dimension of this layout is 3.25 inch in length and 2.5 inch in width. We follow the standard of IPC 2221A for our PCB design. And we also order the PCB prototype to be printed at JLC PCB.
To determine the power supply needed for the ICT, we added the approximate power usage for each of the toy's electronic components plus a 30% margin as advised by Dr. Wei. This 30% margin would cover leakage current and various voltage drops. We reasoned that the batteries should power the ICT for about 8 hours on a full charge. This would allow enough time for entertaining cats during a typical workday. We compared nickel metal hydride and lithium-ion rechargeable batteries as a power source for our project and selected nickel metal hydride due to its lower volatility and cost. We selected a rechargeable battery because that is the standard for most electronic cat toys today. We considered 6, 4.8, and 3.6 volt battery packs with similar current ratings. And while we would have preferred to go with a 3.6 volt pack, it was out of stock, and other 3.6 volt packs that were available on the market did not offer more than 1,000 milliamp hours. This would only guarantee powering our device for about 3 hours. We could have a battery pack custom made, but we will need to research that option. For now, we decided to go with the 4.8 volt battery pack for our prototype. This pack is a good fit with an acceptable weight at just under 100 grams. We designed a voltage regulation circuit with the help of TI's WebBench Power Designer to accommodate boosting power from either a 3.6 volt or a 4.8 volt battery pack. The voltage regulation circuit utilizes a switching regulator to boost the voltage to 5.2 volts. This is recommended to properly supply our MCU with enough voltage to power a 5 volt voltage bus. Our next step was to consider, should we design and build a battery charger for our battery pack? Nickel metal hydride battery charging is significantly complex. Basic charging circuit components include regulated AC to DC power supply, current control circuitry, a voltage regulation circuit, and overcharge and thermal protection circuitry. Should we undertake designing and building a charging circuit for our battery, a considerable amount of time would be required to study the various charging techniques used for the process and to perform testing. Building this circuit is almost a senior design project in itself. And currently dealing with component supply issues, it would be even more difficult to compose such a circuit. Due to the complexity of designing and building an NIMH battery charger, we decided to use the prefabricated USB charger that is sold with the battery pack we selected. These USB chargers come with built-in overcharge protection and an indicator light to alert when charging is complete. This seemed to us to be the optimal and safest choice of charging for our project's power supply. The power supply circuit for our project is designed to be able to be switched between two positions. The first switch position being off or recharging the battery, and the second switch position enabling powering the toy through the voltage regulator. Switching for our power supply circuit is realizable with a single pole double throw switch.
These are some of the standards that we apply in our hardware design of our interactive cat toy.
Software design. To make our project successful and fully functional, we need to use an application software and embedded software.
This software block diagram shows when the program begins, it starts by connecting to the Bluetooth device. It then checks to see if there's any input from the mobile application via the Bluetooth. If it does not get an input, it runs the base program's LED pattern, sound, and tail motion. If it does get an input, then it updates either the LED pattern, sound, or tail motion, depending on what was selected in the application. After running either the base program or updating program, it will check if the device is turned off or put on sleep. If the device is not off or on sleep, it will check the application input again. Otherwise, the program will end.
Application software. Our application is created in Android Studio. Creating apps for iPhone will force us to own a Mac, but with Android Studio, we could create apps in different operating systems, Windows, Mac, or even Linux. Also, there are more users around the world that use Android and not Mac. Based on the statistics from last year, Android is still leading the market with 70%. We are using Java is because there is a great amount of libraries and tools that could make it easier to create apps and be able to connect it with our toy and its features. Next will be the graphical user interface. This is how our application is going to look. The front page will have a clickable image where it will allow us to connect to the Bluetooth module. This part we're still working on it. After our app is connected to the toy, it's ready to use. It will send the user to a different page where we'll need to choose the features that wants to use. Could be changing the colors of the LEDs, send sounds through the toy, or move the tail in a different speed. Application capabilities. With our app, we want it to be user-friendly and easy to use. We believe that creating an app, the cats will have a better experience with its toy. Also, right now we are running the app on a simulator, but soon we are going to use a physical phone to be able to test the Bluetooth connection and be able to display the different Bluetooth available at the moment we try to connect. For application standard, these are the standards that will apply to our application development. For wireless communication, as we mentioned before, we are using a Bluetooth module. The version that we are using is the HM10, which is a low power and could be also compatible with iOS application. We took this decision because at the time we were not sure what operating system we were going to use. There are many options out there for Bluetooth, but the best recommendation is to use a module version 4 and above.
The lighting effects of the interactive cat toy will use the WS2812 LEDs. These provide a wide range of RGB color choices. The base model will have one color going down the LED strip, while the application will either have the choice of 3 colors going down the strip or a rainbow of colors going down the strip. To emit light on an RGB LED, it requires some current control. This is to avoid any LED burnout. To avoid burnout, we use a 50 ohm resistor between the MCU and the LED strip. Then, using the embedded software, we limit the lighting effects to use 60 milliamps. The code to the left shows the basic idea of how we will be programming the LEDs. The tail motion of our interactive cat toy will be utilizing a microserver motor to provide the tail wagging effect. The base model will simply move up and down at a steady speed, while the application will give the options of moving up and down halfway to up and down full way at a steady speed, or a quick movement of up and down. An added benefit is that we will add catnip to the tail, and the motion will set off a nice aroma of catnip in the air. The position of the servo motor will be grabbed using the nanosecond method. This will allow for a wider range of angles of the servo. While 500,000 nanoseconds gives the position of 0 degrees, 15,000 gives a position of 90 degrees. The CircuitPython code to the left shows the basic idea of how our code will look. The initial position will be set to 0 degrees using the 500,000 nanosecond, and then continue on an infinite loop, moving the tail from 0 degrees to 90 degrees, pausing for a minute between each motion. The stemma speaker of the interactive cat toy will be able to make many sounds that entice cats. The base sound will simply be birds chirping on a loop, while the application can either be the sound of bugs flying or the sound of squirrels chattering. For CircuitPython to be able to emit sound from the speaker, we have to decode the MP3 file into a static array of numbers. After the MP3 file is decoded, we can play the sound through the speakers endlessly through an infinite while loop. The sensor of the interactive cat toy will establish the ability for sleep mode. This will allow the battery life to last even longer. With no interaction from a cat for a short while, the interactive cat toy will switch into sleep mode. When the cat triggers the sensor will send a message to the program to wake up and continue the base toy LED pattern, tail motion, and sound effects.
Our work distribution table represents how work for our project was shared among our group members. P distinguishes the primary and S the secondary members who are responsible for an area of work within our project. The cost to build our interactive cat toy came in at just under $200. Our project is being fully funded by our group members, having each student agreeing to pay 1/4 of the cost for the project. Our current progress to date has brought us to within approximately 60% completion of our senior design project. While we still have a lot of work to do to get our interactive cat toy fully operational, we believe that we have made good progress and will be able to finish on time.
Here are our challenges while designing the interactive cat toy. We need to consider the battery size and its safety. Nickel metal hydride batteries are generally safer than lithium-ion batteries, as lithium-ion batteries can blow up if overcharged. However, it is also bigger and heavier. We also are having trouble fitting all components into the chassis. This problem will require us to spend more time designing the hardware layer. Moreover, the components are not working as intended, such as noisy audio from the speaker and the PIR sensor is not too sensitive under the skin. Finally, many components are out of stock due to the pandemic, which forced us to find alternative solutions.
Throughout the initial interactive cat toy design pitch, our group made a great effort into understanding what cats like and what they dislike. We also took into consideration the consumption of power and the size of the toy. The decisions that we kept was retaining the size of the toy to a relatively small frame, about less than a foot. We also kept a mobile application feature. This will allow for the cat to have more options and to stay entertained. Changes that we made was from a laser to an LED. Lasers tend to be larger in size, and with the assembly of the other functions, made the device relatively large. We also changed from just a simple squirrel skin design to a custom interchangeable skin. Though this is not hardware related, our team thought this would be a quite fun touch.
Next steps. Test PCB connection with power supply, switching and components. Refine component fittings, chassis design and exterior skin patterns. Refine embedded programming for multiple feature expressions. Complete phone application GUI and ensure functioning control of toy feature through Bluetooth wireless communication. Ensure ICT meets requirements specification.
This concludes our presentation. We appreciate you taking your time to watch. Thank you.